So good afternoon and welcome to this session on urban air mobility and advanced air mobility #1. My name is Dirk Schäfer from the EUROCONTROL Innovation Hub, and I said in the plenary that we will be starting and finishing on time, and I intend to live up to that promise. So I would like to introduce the first of two speakers we have here in this session before the coffee break, Henk Blom. Henk is a fellow IEEE and an emeritus professor in ATM safety from Delft University of Technology. And he has a research interest in formal modeling, stochastic analysis, and rare event simulation in performance evaluation of socio-technical ATM systems. His talk today is related to the safety risks to persons on the ground that are impacted by UAS operations. Henk, the floor is yours.
So I shall try to share my screen.
Yes, please.
Welcome, everybody. So good morning to participants from the United States. Good afternoon to persons in Europe, and good evening to participants from Asia. So I would like to talk about safety risks posed to persons on the ground by US-based services, in particular when you look at commercial US-based services. And they can really learn from airports and hazardous installations. And that I want to tell. Is my next page. No, let's say this one. Yeah. Okay. So what you see that a commercial US-based operation, it offers service to public or company, for example, parcel delivery service or air mobility service, and there are more of them. It's typically within a certain area. It makes use of multiple US types, and it typically conducts a number N UAS flights per year. I introduced already the capital N here. I will use it later on. Important is that there are societal issues. There's a very nice EASA report a few months ago published, and they identify as societal issues the safety risk, the noise hindrance, privacy, security and cybersecurity, visual pollution, and other environmental pollution. Of course, if you see it from now, because there are not so many US flying, you can hardly imagine visual pollution or noise hindrance or safety risk or privacy. But if the use is going to increase, then at a certain moment you start to wonder, why is this drone every day flying over my property? And you start to be concerned regarding privacy. And then you read in the news that sometimes these things drop off the sky and end up somewhere in a garden, and then you start to think about safety risk. And if they fly low, then maybe you have noise hindrance. So it's very important that these kind of things are being thought about before we're in a situation and people cannot do anything anymore. So the important thing, of course, there's an unresolved gap that the societal risk issues are more severe for areas with more potential customers for the commercial operations. So what I will address in this is first third-party risk indicators, then the impact on the requirements on the US operations, then I take last mile delivery examples, and then I go to conclusions. So first, the third-party risk indicators. In commercial air transport, there are in fact a number of third-party risk indicators. One is the third-party risk related to a flight. It's expected number of ground fatalities per flight or flight hour. And these make out a small part of the expected number of fatalities per flight or flight hour. If you look at statistics from accidents in commercial air transport, then these are all well counted, but you really see it's just a fraction of the fatalities. Most fatalities are first party and second party. So second party are the passengers on board of aircraft. Then you have societal risk indicators. They are used for airports. One is an FN curve, that's the probability of N or more ground fatalities per annum. And the collective risk is the expected number of ground fatalities per annum. So per annum, that means you look for an airport to all the flights in a year, and the same for the collective risk. And the other one is individual risk. It's the annual probability that an unprotected person at location Y, that is the full year at that location Y, is being killed due to an accident, of an aircraft accident. And these indicators are also used by hazardous facilities and by airports already announced. So there is reference material to be used for US operations. It's important to see that the third-party definitions differ in some way between commercial air transport and in US. In commercial air transport, third-party are people exposed for reasons unrelated to the flight. That implies that it's the public on the ground. And for US, it's the people not associated with nor deriving direct benefit from the flight. And that means that concerns public on the ground, but also passengers in another air vehicle. So if the US hits another air vehicle, then passengers that may suffer from that in the other air vehicle also are counted as third party. Now, using this, we extend the TPR indicators from commercial air transport to UAS. And take into account that we only look now at the ground risk. We don't look at the risk that the US has on passengers in another flight. So the collective ground risk per flight, I refer to this as the RC ground I from the ith flight. And it defines expected number of third-party fatalities on the ground in a given area X due to the direct consequence of the ith UA flight accident. You can also do it then per flight hour, then you divide this RIC ground by the duration of the flight. I introduced these RI, it looks now complicated, but to make it easy later on. So now we define collective ground risk. That is the expected number of third-party fatalities on the ground in a given area X due to the direct consequences of UA flight accidents during a given annum. So we look at the whole year like it's done for airports. And we call that this R with superscript UAS and subscript C ground. That means that this one is just summation over all US flights in a year, IS1 to capital N, over the RCI ground that was here at left defined. We also define the individual risk for US. That's the probability that an average unprotected person who resides permanently at ground location Y would get killed due to the consequence of your flight accidents during a given annum. And of course, here you also get that for the Y, it can just add up the individual risk per flight, and then overall the capital N US flights. So that makes it relatively simple to connect the new things, the collective ground risk and individual risk, to the one that's already used in US literature, that's the RIC ground. Now let's look on impact on the requirements, because you can always get things safe if you put higher requirements on the US operation. So first of all, we introduce acceptability thresholds for the 3 US TPR indicators. In the US literature, they typically look at this collective risk for ground per flight, US flight, divided by the duration of the flight, and that must be smaller equal the criterion CE loss, and that's the equivalent level of safety. So the CE loss is then derived from how it is in current commercial operations, so for manned aircraft. For the collective ground risk, you must have this smaller equal the C of collective ground risk, and this C collective ground risk can be derived from the criteria that they use for airports and hazardous facilities. And for the individual risk, then this one must be smaller than the C individual risk. And also this one can be taken from the regulations on individual risk for airports and hazardous facilities. So it's clear if you have these inequalities, so thresholds, then they can be used to get requirements on the overall US system failure rate. I call it gamma E. That I will show you next. So from the 3 ELOS, CCIR, and IR acceptability thresholds, we get to requirements on overall US system failure rate, gamma E. And there are 2 methods to do that. One is to run a Monte Carlo simulation of a US operation, and that has been addressed, how to do that and how to use the models, have the right models in a recently published journal paper. And we illustrated the working of it for a hypothetical US-based parcel delivery service in the city of Delft. And the second method, that is the analytical characterization for parcel delivery under model assumptions. And that is the current paper in my presentation about. So then you must make a number of assumptions. One is homogeneity assumptions. For example, a constant population density over the area you consider. That these have always also been used by others before, like by Melnick and all in 2014. Then we assume that the deliveries area is a circular area around the delivery center. We have an expected number of parcel deliveries is the same for each inhabitant of that area. The delivery flight follows direct radial paths out the center and back to the center. And the crash center is uniformly distributed along the radial and Gaussian across the radial. So relatively simple assumptions, but not too strange. The most hard assumptions affect the homogeneity assumptions. I can come back on that later, but for now, this presentation is if you assume homogeneity. Otherwise, you must go to Monte Carlo simulation. You cannot do it then in an analytical way anymore. So now I look at the method 2. If you do the right analytical evaluation, you get the 3 requirements, ALOS, CGR, and IR-based requirements on the gamma E as a function of model parameters theta. So you get for the ELOS-based, you get gamma E smaller as the CE loss divided by a function of theta. It's a function of ELOS of the parameters theta. The same for CGR and for individual risk. So I don't go into the equations. The equations for the F are in the paper, but I don't go to look at them now. Let's look at how they depend on the parameters. So in this table, there is for the ELOS based, for the CGR based, and the individual risk based. And the parameters look at the size of the crash area. The ELOS base, it's linear, linear, linear. So if the crash area increases, then the inverse of the gamma E, of the lambda E, dus the overall rate, increases linear with the size of the crash area. For the probability of fatality, of the human fatality, also all three have a linear relationship. If you take the population density into account, then we see difference. For the E-loss base, it's linear. For the individual risk, it's also linear. For the collective ground risk, it's quadratic. The explanation is as follows. If you have the E-loss base is only looking at if it drops, then it multiplies with the population density. At the IR based, it is because if the population higher, then the chance that the US is coming there increases with the population density because it has to bring more deliveries. And in the collective ground risk, it's quadratic because it takes both this effect, and then you get a quadratic effect. Then the probability of no shelter protection, that's linear for E-loss and collective ground risk, and it's not related to individual risk. Then the mean number of deliveries per year per inhabitant. There is no relation for E-loss. It's linear for collective ground risk and also linear for individual risk. Then the delivery radius has no impact on E-loss. It is cubic for collective ground risk and quadratic, so cubic to the third power and to the second power for individual risk. Then the radius of the zone, I mean the area around the center, delivery center. There you say, stay away. We know it's quite unsafe there, so stay away or inside the building. The E-loss base doesn't take into account the collective ground risk neither. And for the IR, individual risk, it's about inverse linear. Then the cruise speed of the US in delivering, it has no role in E-loss based. It's inverse linear for collective ground risk and inverse linear for individual risk based. So you see that there are a number of important parameters where there really is a relevant difference. Now let's take a last mile delivery examples because you have these general equations and you can apply it to many kind of examples. I just do a few examples here. Maybe good to see, I take parameters. These I took from the application we did for the city of Delft. So we had a range of almost slightly more than 3 kilometers. The zone around the center was 100 meters. The cruise speed we used 50 meters per second. The size of the crash area 1 square meter, so not too large drones. The probability of fatality we had 1, that is the Feinstein model. And the probability of no shelter was a probability of 1/10. Then we had 3 area types. Urban, that's more or less the city of Delft. Then you have a total number of persons within this radius, 120,000. Metropolitan, you have 300,000. And the major city center, you had 840,000 persons in that area. To give an idea where we're looking at. Then we take for the criterion to see E-loss. We have this value, and that is coming from Cloutier and Walker. They did a very good study on that already in 2006. The C, collective ground risk, we have this equation for it, where the C is coming from the FN criterion for 1 or more ground fatalities. And the CIR we get from the individual risk criterion in multiple countries. So this FN criterion is also used in multiple countries. And the exact figures, it's not so relevant now. Let's go on here. Now I show how, as a function of the mean number of deliveries per inhabitant per year, what is the effect on the lambda E requirement. I have here lambda E, not lambda minus E. That means if the N increases, the lambda E requirement is going down. If you had lambda minus 1, it would go up. I should have done that, but sorry. now it's important that we see three curves. One is for the ELOS, that's the dotted line, the dashed line. Then the dotted line, that is for the individual risk. And the curve that lies highest is the collective ground risk. The lower the curve, the higher the lambda E requirement. So if you have very few parcel deliveries per person per year, then the ELOS is the highest highest requirement. But at a certain moment, here's the takeover point. And that is for the individual risk when the mean number is 0.8 parcel deliveries per year. And for the collective ground risk, the takeover point is at 2.44 parcel deliveries per year. If you look currently at what you see being delivered at your house, I think it's something like one per week or something, then these are really low numbers. That's where you see you get break-even points. And this for an urban area. Let's do the same for a metropolitan area. Then we see that the ELOS and the IR lines stay the same. The collective ground risk is going down. So now for the collective ground risk, the takeover point is at 0.98 parcel deliveries per year per inhabitant. And if we go one step further to the metro city center, then again the IR and the ELOS curves are the same, but the collective ground risk requirement is even going lower. And then the break-even point is at 0.35 parcel deliveries per year. So that is the nice thing of these equations. Having these analytical equations, you can rapidly see what it means. Of course, under all kinds of homogeneity assumptions. Let's make another comparison. For that, we say, assume that the ALOS-based lambda E requirements are posed through regulation on the US, and then slowly the number of parcel deliveries per year, the average, is increasing. First 1, then 10, then 100. Let's see what happens. Because you have seen that the break-even point of ELOS in the zero risk is independent of the population density, so we can have the same results for any area type. So even from rural to metro city center, the next results to show always apply. The only requirement is the homogeneity assumption. Now, I also apply the Schiphol rules. I interpret them using the Schiphol rules regarding individual risk criteria. And these are, if you are above the IR threshold, then no new housing developments can be done there. When you are within a factor 10 from the threshold, then housing is stopped. And if you are in between, then people that live there, there are no new housing, but they get a waiver to remain in their housing. So these are the rules applied to Schiphol. And around Schiphol, if you apply these rules, then it appears that also the collective risk, so the FN curve requirements are also satisfied. So Schiphol mainly uses these rules together. So let's apply them now to the US situation. So we make an individual risk map for the N is 1. So on average, 1 parcel delivery per person per year. And we use the ELOS-based lambda E requirement. What do you get? You can look at the colors, but important to look at these circles in the middle. The smaller circle, that's only a dot here, that has a radius of 40 meters. And the larger circle, that's the only one you see not as a dot, that has a range of 139 meters. And you see in that case, there are 0.2% that receive a waiver. Now let's look at the next case for N is 10. Then you also see circle areas. The inner circle is 139 meters. So 0.2 stop of user house. and 90.3% in 30-90 meter radius receive a waiver to continue staying in the house, but no new housing development. And if you go to the Metro City Center, if you go to NS 100 parcel deliveries, then the whole area must get a waiver or even stop housing. That's 95% must stop new housing development. Or stop, no, stop. No, they must stop housing, so leave their house. Of course, in practice, this is unacceptable. Okay, let's go to the conclusions. So there's an existing gap that societal issues in areas with more potential customers, and there are different ones. I only looked here at safety. And in US literature, they have only addressed TPR from a flight perspective, while airport and hazardous facilities consider all annual flights operations. And that leads to novel TPR indicators and thresholds for individual risk and collective ground risk. And then we have shown there are two assessment methods. One is Monte Carlo simulation and analytic characterization. That analytic characterization was the subject of my talk now. Then we applied it to the last mile parcel delivery under 3 different requirements. And the evaluated examples were for urban area, metro city. And then you see that the takeover points are pretty low. And if you have under ELOS based Lambda E and 10 parcel deliveries per person per year, then about 20% of the area has a too high individual risk. And if you go to 100, then the full area has a too high individual risk, and about 20% must even leave their house. So that's would be completely unacceptable. So the conclusion is that for a commercial US parcel delivery service involving manual and annual flights, an ELOS-based Lambda E requirement doesn't comply with TPR regulation that has been developed for airports and hazardous facilities. Then there is follow-up research, for example, to incorporate, make it explicit, the ground risk of mid-air collisions between 2 delivery US and delivery US with another US or low-flying general aviation. Then also extend the analytic approach to other types of US operations, for example, flying taxis, medical drone services, to evaluate the TPR effects of advanced UAS support systems. For example, when you do risk-based optimization, minimization of the risk through the US flight path. And to improve third-party risk submodels for UAS. That's the descent of the US to the crash location, the probability fatality models, the shelter protection. So on all these areas, there really is room for improvement. The one I have been focused on the PSD is on probability of fatality. Then that's my presentation. Thank you. Any questions?
Excellent. Thank you very much, Henk, and thank you also for being perfectly on time. I knew I could count on you there. We have a few questions, and I'd like to start this off with some of your assumptions, specifically when you calculated the individual risk, and you said it's independent of the population density. You assumed homogeneity, right? And that assumption, of course, is not always fulfilled. Likewise, you assume for the individual risk assessment permanent residency, which is also probably leading to an overestimation of the risk. So I'm wondering whether you could discuss how sensitive your results are to these 2 assumptions.
It depends what you look at. It's clear that if you don't want to use these assumptions, then you must do it through Monte Carlo simulation. You can use the complete variety in a city of population density and other kind of things that vary over a city. Of course, then you have the disadvantage that you cannot do it rapidly. And you cannot look at many different cases like curves I had here. These kind of curves you can rapidly make with the analytical equations, and you can do for all kinds of variables here. You can rapidly see what's the effect, and that's very helpful to do. If you would like to make these kind of curves with the Monte Carlo simulation, for so many cases, it will take you a year or something, yeah? So it's very difficult to do that. So that's the power of having analytical equations. Of course, then you must take into account that you have these assumptions, yeah? But of course, if you know these assumptions, it's not so difficult to reason about it. And in particular, if you also can say, okay, to understand it, let me run a Monte Carlo simulation where I do deviations from this. You rapidly can see, you get an impression what's the effect. So it's not a big limitation. Of course, because you gain so much and you get insight so rapidly that it is impossible to get at that scale from Monte Carlo simulation.
Okay, I think you answered the question that was posted in the Q&A kind of in passing, where the question was to compare the strong points and the weak points of the Monte Carlo simulation as opposed to the numerical method that you've presented here. And I hear you say Monte Carlo is more precise because you can loosen some of the assumptions, but you run lots of Monte Carlo simulations that's quite numerically intensive and takes you a much longer time. Coming back to your assumptions and the assumption of permanent residency that you assume for the individual risk, is this also an assumption for the collective risk assessment? And do you have a feeling for how much you overestimate the risk if you assume permanent residency?
Okay, it's good to see that in this list, the first one, the homogeneity assumptions, apply to all three. So the A loss, the collective ground risk, and the individual risk. The next four bullets, the circular area, expected number of parcel deliveries is the same for each inhabitant. Delivery flight follows direct radial paths, and the crash center is uniform distributed along and Gaussian cross radial. These four you don't need for the A loss. And why not? Because the A loss doesn't take any of this into account. And exactly the collective ground risk takes the circular area into account and the expected number of parcel deliveries. And the individual risk takes, in addition, delivery flight follows direct radial paths and the crash center relative to that radial. That's for the also, in addition, that is needed for the individual risk. So big difference regarding assumptions don't apply for the three different approaches.
Mm-hmm. And when you speak about the crash center, do you assume that the UAV is just dropping from the sky like a dead bird, or is there some sort of mitigation or some sort of emergency trajectory assumed?
In this one, we assume that it is somewhere dropping, but under the influence of the wind from the sky, and therefore you have a Gaussian. If you have a clever UAS that don't drop in that way, then of course the risk can be low. But here I assume now the most simple type of drop, that they fall straight under influence of the wind to the ground.
Okay. The second question I would pick from the Q&A box is, how do you see the analysis in this research being used in the context of USpace? So what are the proposed next steps of including your calculation and your estimation approach in USpace?
The main thing, what I see is that's in the follow-up, because once you start for a while working on this, you get insight in kind of things that are currently, where the models, the submodels are kind of weak. One of it is the probability of fatality. So I've focused with another PhD student and now continued with Shengpeng, the co-author of this, on this point. And we find really surprising things. And for that, we use multi-body system models so that you can exactly see where the drone hits the human, etc. That can have a lot of influence on the probability of fatality.
And is the geometry of the drone, how are the assumptions and how are those taken into consideration? Because the size and the mass of the drone, of course, and its behavior will have an impact on how likely it is that somebody on the ground is crashed. Not only the population density, but also just the pure mass of the drone. And there, I assume you have to make certain assumptions. How are these taken?
For this one, for probability of fatality that we have developed with another PhD study, that the drone is well modeled in a multi-body system model. So all the different parts of the drone are separately modeled.
And which assumptions do you make about the, if you like, population of drones that will be flying? How many, which percentage or which number of class 1, 2, or 3, or how heavy are the drones? What's the distribution of heavy versus light drones that you are assuming in your calculation?
Okay, for this one, for the extension of the probability of fatality, then with the multi-body system, then you are already happy to have a proper model, multi-body system model for the drone and the human per drone type. So to have them all, it will take some while, that's for sure. If you use the current models for probability of fatality, they are very generic models and they only take into account the mass and the crash velocity of the drone.
Mm-hmm. Okay, do you assume that person on ground wear helmets? No,
if they wear helmets, they have protection. For example, if a drone hits someone on a motorcycle that wears a helmet, then of course it has partly protection. Of course, if it would happen with a commercial aircraft that falls on that, then the helmet will not do anything. But if you have small drones, then for sure a helmet has a lot of protection.
That gets very complex. I'm just wondering, last question I would have to ask you, Henk, is which indicators, which third-party risk indicators are presently used actually in existing regulation, for example, EASA or the FAA itself?
Yeah, I have a few reserve slides and I can show you what I have here. A table is what EASA YARS is doing. EASA YARS for AMC APAS. Then the FAA AC, the FAA order, and an SMS manual. Now, if you look at the FAA, the SMS manual, then it looks at all the type of contributions. I can show you the fatality types. It has to do with, are you looking at persons on the ground, fatalities on the ground, or persons on board? And also, what type of accident? Is it the UAS crashing to the ground, or UAS hitting another and that is then crashing to the ground, etc. So in many combinations, I can show you them a slide back, but they are also a paper we published 1.5 years ago, a conference paper. Then you see that the FAA SMS manual addresses all these cases, but from the eye, the flight, single flight perspective. So not summation over all the flights in a year. But if you look at the specific developments at FAA for US, then you see that they focus only on this one, the things on the ground, and the other ones not. In the EASA, similar. You see the focus on this one, and it has something on board to take into account. For the certified category, that's like they do currently certification of commercial aircraft. That's pretty good. For the light certified The ground risk, they have it also, special rules for it, added. And for the SORA, they also do something for this and this, but it's very qualitative. It's very difficult to get a quantitative hold on what exactly is doing. But you also see that many areas where there's also risk are empty, not addressed. According to the SMS manual FAA, you should address them.
Okay, excellent. I'm sure our FAA colleagues will be delighted to hear this. We're running out of time. Henk, thank you very much. I would give you a virtual clap of hands for the presentation. And we will move on to the next presentation, which will be given by Hartmut Fricke. And I think we will share the presentation from here because Hartmut is in a dark room with very poor internet connection. So whilst Radan is trying to crank up the presentation, let me introduce Hartmut. He has obtained his PhD in aeronautics and astronautics in the Technical University of Berlin. And he is the head of the Institute of Logistics and Aviation at Dresden University, TU Dresden. He's also a longtime champion of the ATM Seminar 5K Fun Run, but he was beaten last year by Xavier Olive from Honora, and that still hurts, doesn't it, Hartmut?
Thank you, Dirk, for mentioning and pointing to this very important fact.
All right. Do we have the presentation up and running, Radan?
Yeah, I'm going to share it now.
Okay, thanks very much.
Dear Mr. Chairman, thank you for giving me the word. My talk about mid-air collisions with drones is a joint work of TU Dresden, Kinetic Limited, are located in Great Britain, and the GFL, a university spin-off company located in Dresden. I have the honor to present this piece of work on behalf of my colleagues, Abel Austin, Christoph Thiel, and Robert Brühl. My colleague Stanley First, however, will hop on and later present the use case findings. This talk will be twofold, where the first part is covering investigations on drone collisions with manned aircraft regarding probabilities and severities on potential collisions, depending on the selected impact scenario. The second part is about using our agent-based modeling and simulation environment from TU Dresden to apply the data generated in the first part to an urban use case scenario around Dresden Airport, where commercial transport is operating in close vicinity to simulatedly passing drones. I may point to the fact that the first part is an activity endorsed by the European Aviation Safety Agency, EASA, whereas the second is a TU Dresden-led research activity. So let's set the scene. You may wonder whether the topic addressed in this talk, entitled Collision Risk with Drones, is really worth to be studied, right? One might think that typically drones fly at low altitudes, in a few 100 or 1,000 foot, so that commercial air transport should generally be safe. But let us look into statistics. These tell us this is really a growing problem. At the pre-pandemic times, global traffic performance was around 69 million commercial flights in 2019 alone, recorded by ADS-B data receivers, on which we then could measure only some 24 drone collisions, and this since the year 2000. However, if you then look back to only the last 10 years, so around 2010, we see that nearly all these collisions happened in that shortened time frame. The trend is thus exponential, and we have to consider the spreading number of new drone units entering service. The global drone market is reaching actually 7 million units, according to Allianz Assurance, from a few thousand units in the year 2000. Taking finally into account the ICAO Europe U-Space concept, where it was decided to operate drones and manned aircraft in a non-segregated airspace environment, we can identify the full dimension of this growing trend of a collision threat. Checking Allianz data once again, we learned that damage to manned aircraft is accounting for 8% of insurance claims above €1 million value. check the colored band on the right. So what is called the foreign object here in the statistics will be mainly be represented by drones in the future. Consequently, and this is far different to aircraft collision risk estimation, severity level determination is a crucial activity to correctly assess the drone collision risk, since we suppose that the severity is less dramatic in case of a collision compared to an aircraft accident, right? So all of this is again reflected in the two parts of the presented research, the severity assessment reflecting the other knowledge part, the probability assessment mainly the theoretical activity. Let's have a brief look on the state of the art in drone collision risk research. Basically, we can recognize that all research considers severity of drone crashes as what we call worst credible, and as such clearly overestimating the computed risk. We do so far the same. However, but as for the probability, we found that all models rely on airspace capacity figures, a given throughput, and, if applicable, the applied separation between the flying units following, for the case of aircraft, ICAO definitions, or if not applicable, if we have a VFR rule environment using subjective linguistic variables like stand clear or stand well clear from each other, as we know it again from VFR operations. With the inauguration of a so-called drone collision task force by EASA in the year 2016, a set of recommendations came along calling for these missing model pieces, such as an analytical model of drone threats and a tethered severity threshold model to deepen the understanding of the effects of mid-air collisions between drones and manned aircraft. And this is exactly what this paper tackles. On the right-hand side, finally, this is just an excerpt of a typical encounter model, which was published in 2011 already by MIT Lincoln Lab in the ATM seminar. Here, risk probability is calculated as a proportion of trajectories in the near-mid-air collision and Mach cylinders in all trajectories in a certain state around the URS. So separation is the main driver of computing the risk. To assess highly detailedly now the severity and probability of drone collision risk, we introduce the term collision envelope, concluding all parameters related to an impact. These cover, of course, typical kinematic parameters such as aircraft type, aircraft mass, operated altitude, speed, but also daytime, allowing us to more precisely relate statistics timely to, example given, sunrise to sunset periods to reflect typical drone operations behavior, or what we see later on, scenarios where we limit wind speed and other. We will create at the end scenarios by using this parameter. ADS-B traffic data and surveillance data was taken from the Open Sky Network encompassing the entire German airspace. And you can see the map on the right side at altitudes up to flight level 120 for the full year of 2019, leading to roughly 1.7 billion data points. See the upper right box for more details on the number of data we used. This was sampled down to 30 random days, filtered for outliers and anomalies. The flight level 1 to 0 altitude boundary is considered to conservatively cover all typical consumer-prosumer drone operations and is based on statistical evidence. This vertical band was finally reduced to flight level 30 and follow-on activities as our use case exploring urban area safety considerations. But for here we start with the flight level 120 band limitation. Since the reference data set is not containing information on the aircraft model itself, the ICAO 24-bit or MODES identifier or the onboard transporter was used to assign the corresponding airframe. In particular, the model and the ICAO type were filtered and to group results by aircraft type, clustered in 8 so-called aircraft classes, following EASA certification specification categories, but more distinctive at the end and also giving consideration to future vertical takeoff and landing configurations such as the volocopter velocity as the multicopter representative and the helium jet as a jet representative. The shown middle figure depicts the statistical expert-driven determination process of this clustering concept for a given for one of the 8 classes, which is called the small jet CS23 category, and where we identified, as we did it for each of these classes, an example aircraft. Here it is the Cessna 510 Citation Mustang. This is the 5th from the left, where the red box is drawn around. ADS-B data contains the geometric altitude above main sea level, as reported from GNSS sensors. However, drone operations are typically reported or related to height. So to derive the height above ground, level information about the topography, so elevation, is required. This information is obtained for Germany from official sources like the Federal Agency for Cartography and Geodesy in the so-called DGM-200 format, with the given resolution shown here on the slide, and the graphics representing the model on the upper right figure. For the study, we processed the historical wind data of all weather stations in Germany, available on the open access file server of DVD, and generated a document containing all wind observations in the year 2019 in a 10-minute interval of all weather stations that you can see on the right-hand side lower picture. Finally, as already introduced, day and night distinction was considered further and reached by following the definition of night as found in the standardized European rules of air, SERA, which is plotted here. Night means the hours when the center of the sun disk is 6 degrees below the horizon. So we use a specific geometric algebra to identify the night and day shift times and located it to each of the grid of the data set. Finally, the aircraft mass was set to maximum takeoff mass and taken from the listed data sources. So basically, EUROCONTROL aircraft performance database with covering some 70% of all aircraft types, followed by the Skyberry repository covering another 20%, and the rest then taken from operating manuals. So to relate the aircraft classes and aircraft examples found in the previous step to the different speeds, we computed those for all of the 8 aircraft classes for a total of 30 days that were randomly selected, from which all data points were taken, but per aircraft class not more than 100,000 per day. After the selection process, the GNS altitude given in the ADS-B data was converted into a height above ground for each selected data point using, as explained before, the digital terrain model, and the aircraft type was matched from the OSN airframe database using the reported ICAO 24-bit identifier of the onboard transponder, as also mentioned before. The processed data will include curves and tables showing mean values, standard deviation, and specific quantiles per aircraft class and height. And you can see those on the right-hand side. Pictures again for example. Class here, the class AC3, which is the light jet CS23 category once again. The 3 figures in a row right below show the speed distribution for selected altitude bands, fitted with acceptable normal distributions to allow analytical processing in the upstream process. So if you would like, the middle graphics are something like a vertical cut through the graphic on the upper part for a given altitude band, typically covering 500 foot. 3 scenarios based on daytime and wind maximum were further studied and compared to and introduced reflect specific drone operating behaviors. So at this end, we decided, however, to continue with the baseline and no wind speed or daytime restrictions applied, since variations were found to be quite small. So this exercise was interesting, but let's see, probably not that relevant. And in the range of a few knots only. This can be seen on the lower graphic left and right. So for the left, we can see that the difference for fixed wing aircraft are as expected. In the low wind scenario, the average ground speed is a little higher than the baseline scenario because low altitude operations, approach and departures are mainly conducted against the wind. This is our assumption. And the cause for the contrasting behavior of large helicopters like the aircraft class 7, so the second box from the right, is unknown, but could be justified with a combination of the examples. While in the low wind scenario, we had 97.5% of data points originating from the Eurocopter 45, where the cruise speed is about 135 knots. In the baseline, we had only 85%, but 4.9 from the A139. And so we have different samples, and the right picture, however, in contrast to the left one, basically only shows no difference between the safe drone operation scenario and the baseline. But this is rather statistical noise, what we can see here. But the exercise was supposed to be done since we were really fearing that we probably had to restrict the data sets timely. But again, as you could see, it's not that critical for the moment, so we can go ahead with the baseline scenario. So only selecting randomly days without any time limitation. For all classes, we can state that the statistical analysis showed expectable behavior for all aircraft classes, all of the 8, with mostly increasing ground speed with increasing height or altitude and main aircraft size. So now let us look at the drones. We described how the probabilistic distribution of aircraft ground speed was calculated as a function of altitude, right? So this provides an evidence-based justification for the speed of different categories of aircraft during low altitude phases of flight, rather than relying upon generalized performance figures. When considering near-mid-air collisions, so we introduced already the term NMAC with drones, the relative velocity of the drone of the aircraft is a second most relevant risk trigger, obviously, so dictating the kinetic energy. No similar database of drone movements, however, is available, so an alternative approach was developed based on a database of drone sightings or near misses collated by the Aviation Safety Network ASN. This database contains over 12,000 entries actually, documenting worldwide drone sightings from aircraft and on non-confirmed collisions. So it has constantly been compiled from a wide range of reference sources, and a query of sighting altitude over frequency produces the logarithmic type correlation as shown on the upper right figure. To emphasize on the growing relevance of drone risk, the same database allows to sort chronologically sightings, especially those judged as near misses according to the right and lower figure. And again, we see this exponential behavior, let's see this way, since the year 2015. For the use case presented later, we already show here the green line, which limited all altitudes to something like 3,000 foot, indicating that the relevant portion is found below the 2,000 foot height bandwidth. For similar reasons, we relied on subject matter experts and OEM data to derive typical drone velocities with a typical speed of e.g. 23 meters per second for fixed wing and 50 meters per second for multicopters, is shown in the lower table in more detail. With this, we are complete in estimating the collision speeds for aircraft and drones separately as a function of altitude. So before doing another step, to compute the collision risk combined, we first check again the severity aspects of such collisions as introduced in the beginning of the talk. Local manned aircraft target identification, so it means where hit the drone the aircraft, will strategically involve finite element model simulations and testing of collision scenarios. That's obvious, and this is going to be covering the next steps in the vulnerability program of EASA. But for the first hand, it would not be practical to consider impacts against all potential impact sites on each aircraft class, because this would lead to a huge number of possibilities. So we instead prioritized the local impact zones of interest And a list of candidate impact zones like windshields, propellers, leading edges was created based upon outputs from EASA's Drone Collision Task Force and other studies. For each example aircraft identified per aircraft class, you remember for the first part of the presentation, these zones were then again evaluated to the criteria relative probability of the feature being impacted, the perceived vulnerability of the feature to impact and damage, and the criticality of the feature to the safety of the aircraft and its crew and passengers through workshops and offline surveys. Let me say the conditional probabilities assume that a collision has occurred and considered the relative probability of each of the candidate impact zones will be struck. Vulnerability of the impact zones and the ability to withstand an impact without failure was based upon, again, expert opinion and evidence allocated to a 3-level determination process like high, medium, low. The perceived safety impact, so what we call the criticality of the impact zone being damaged, was classified then on a 4-point scale from low to extreme, like immediate grave threat. Finally, a manual process to prioritize the impact zones based upon the combined assessment of these criteria was executed, leading to the list shown as excerpt and the right lower part of that graphic. So we can conclude with that type of approach. We are now in a position to much more detailedly represent the collision risk effects. So the severity level of a potential collision. With that list, that was also represented by an helicopter silhouette on the previous slide, we can now, depending on the scenario modeling, assess collision orientation and speeds using that granular classification per scenario. However, we do not use yet all of these collision envelope parameters in this paper, since considering and limiting us on purely head-on conflicts as sketched on the right upper figure. So basically we could consider different angles on the lateral and vertical plane, but for this paper we stick to head-on conflicts only. For this setting, then we compute the collision risk speeds, compute the collision speeds in a Monte Carlo simulation. It was used to combine the manned aircraft flight data for altitude results with the drone sighting and collision data. This assumed that the distribution of the mid-flight drone sightings is representative of near misses, which could equally have been collisions in the less fortunate circumstances. So the data generated for various quantiles and per aircraft class are listed in the table. You can see on the lower part. And the probability density function shapes on the right graph show the link of the different quantile values and document that the cluster concept seems to be useful, since we have specific and well-distinguishable speed distributions per aircraft class found and presented here on that figure. With that, we are actually now ready for a use case to estimate the collision risk, applying collision speeds per altitude in a setting for the city of Dresden, as indicated in the beginning, focusing on the airport surroundings. And this is what my colleague Stanley Förster is now presenting. I'm handing over to him.
Based on the findings presented so far, we set up a scenario to investigate the collision risks between drones and manned aviation aircraft. For this purpose, we utilized an agent-based fast-time simulation environment which has been developed at our institute for over 10 years now. It constitutes a framework that gives the possibility to set up arbitrary route structures and airspace elements, and furthermore, the framework provides several agents that behave stochastically and interact with the airspace structure as well as with each other. This is especially helpful to investigate emergent effects that are not obvious at a first glance. The most important agent entities in our scenarios are the airspace users. This includes aircraft and now also drones, which have, for instance, navigation tolerances or variable speeds attached, but also the pilot and ATC agents who mimic human behavior, especially in terms of stochastic delay according to reaction time distributions. Depending on the requirements of the scenario to implement, we also have modeled surveillance infrastructure like radar as an agent to communicate aircraft position to ATC with resolution and accuracy following a probability distribution as well. Finally, we can also model limited communication capabilities due to the number of radio channels available and the speed of the spoken language together with phrase length. In the course of the current investigation and the spaceline scenario, we implemented drone and aircraft behavior without interaction or human intervention. The scenario is located at Dresden International Airport, where we have the final approach on runway 04, which is denoted by the black line in the map on the upper right. For the drone leg, we selected a connection between a small drone depot northwest of Dresden and the downtown parcel center, and the leg happens to cross the final approach segment as shown by the red line on the map. The distribution of aircraft speed is selected so that it matches the altitude of the drone encounters. The diagram on the lower right depicts such an altitude-dependent distribution of ground speeds. Within this environment, we selected a few parameters to create a set of different scenarios. So first, we want to see the effect of a displaced drone leg, where it gets shifted in parallel, as shown by the blue line in the map, so it eventually does not cross the final approach anymore. Second, we vary the altitude of the drone leg, which also shifts the point of where the final approach is crossed until the drones completely fly above the final approach. Then, in lack of actual data regarding the navigation accuracy of a drone, we decided to select the actual navigation performance to be 5 or even 10 times worse than that of an aircraft. Finally, we also set up a nominal and a high load traffic scenario. Combining all these parameter variations resulted in a set of 112 scenarios, and each of this has been simulated to comprise 1 million flight hours. The results of these simulations are depicted in the diagram to the right, where we see the collision probability per hour for each of the 112 scenarios. What's quite obvious is that the influence of the traffic load, which is depicted by crosses for nominal and circles for high load scenarios, is very low. So the nominal scenario has still a little less collision probability, but the difference is quite insignificant. Therefore, we can conclude that the idea, for instance, to limit drone traffic in favor of no-fly zones may not be as effective as expected. Second, we can observe that the lateral or vertical separation of drone and aircraft flight legs are the most significant countermeasures to enforce safe operation. What's however most interesting is the observation that for scenarios where the drone leg and the final approach are very close together or even intersect, see for instance those blue dots, the probability of collision is higher in case of higher navigation performance. This is called the navigation paradox, where high navigation accuracy leads to high concentration of traffic along the intended flight leg, but therefore also to a high concentration at points of intersection and thus a higher collision probability. And the effect of traffic dispersion in case of lower navigation accuracy then also leads to lower collision probability in these cases. Finally, we see that the overall collision probability in our scenarios is relatively high, but we did not yet consider the impact geometry and severity of such events, but imply a fatal collision in every case instead, when however the majority will be of limited impact depending on the impact parameters.
So with that said, for the use case, let me conclude the talk on the major findings we can see so far. We had performed the big data exercise based on ADS-B. including fusion of multiple unrelated data sets. As you saw, it's about the terrain model, the wind data model, and much more, to provide a probabilistic assessment of potential collision speeds. And this was coupled to identify common aircraft types and exercises to define what we call a collision envelope. So a lot of parameters indicating the driving parameters per impact scenario to provide a robust foundation for the ongoing activities, evaluating collision scenarios by validating modeling and test in a major European research program led by Kinetic and awarded by EASA. Tristan used the data to assess aircraft drone collision risk using an in-house ABMS tool already used in other EUROCONTROL studies and ready to consider more detailed drone collision severity models. Important to see the outcome that Stanley was presenting. The probabilities we computed are as high as 0.9 times 1, so 90%. So we are close to 1, which is a very surprising outcome, and it tells us it is all about separating drones from aircraft rather than arguing over capacity constraints or throughput limitations. So constraining drone throughput is not effective, and as a consequence, severity modeling may pave the way to reduce no-fly zone implementation as the only remaining option we see, since the risk matrix on the right-hand side, you can see here, shows clearly that per severity category, which is shown then as a row in that metric, shows that we can afford probability ranges up to 10 to the minus 1 if the severity would lay around small to neglectable. So that's exactly what we look at. And if we could further drop down the probability, then we could generally come to a conclusion that drone and manned aircraft operations could be executed non-cigarettely and still hold at least tolerable risk, what is indicated by the yellow color, but avoiding any red box. So that facilitation of drone business can generally be reached by designing airspace structures based on such operations risk assessment. And we think that this could be a candidate to the specific category operations risk assessment already implemented in the European regulation, or similar methods for drones outside the specific category. So when it comes to much bigger models than the one studied so far, and candidates are certainly the two we just mentioned in the talk, the Lilium and the Volocopter. Measurements on drone actual navigation performance is a missing part in the simulation environment. This is currently a research activity at TU Dresden. We're using a high-end DJI 300 RTK unit and will operate this one under very, let's say, complex urban environments like gusty wind conditions between larger objects like houses or hospitals, and measures the effect of position keeping regardless the environmental conditions. And with that, I'm done with the talk and I'm open for questions. Thanks for listening.
Thank you very much, Hartmut and Stanley. It's interesting you said this is a 28-minute presentation, but it took 33 minutes to play on Radan's computer. So I guess we should get Radan a new computer to speed up our sessions. We have time for a few questions, and I encourage you to type your questions into the Q&A. We have two questions there already. Sandy asks, did you explore variable speed, wind speeds and variable wind directions?
Yeah, Dirk, thank you very much, first of all, for giving me that helping technical hand to make sure that the presentation runs smoothly. Yeah, Sandy, yes, we did. Intrinsically, since we were using our real weather data, as mentioned, from these weather stations shown on the picture, so we got by integration over the path of the drone the different wind speeds per segment of flight, if you like, and this was then considered and respected in the model. Of course, it's just a sample, so it's just a randomly selected day of operations on which we put or placed the trajectories. So one might say, yeah, this could be just an example flight, which is true, but indeed, at least it was covering variable winds as we were staying with the baseline scenario, which has no limitations on wind speeds and also not on the daytime.
What was the source of your assumptions about wind speed variations? Where did you take them from? Were those historical data or were those own assumptions?
This was I was showing you on the graphic. So maybe I tried first this way without showing the figure. It was really German weather forecast data linked to the ADS-B data, which we collected from the OSN database. So it was synchronized data with the day of operations of the aircraft, the weather, and then suppose that the drone would operate exactly at the same time where the aircraft was flying in 2019.
Okay, excellent. Thank you very much. A second question in the chat is, do you see the need for additional data standardization as a means of risk assessment beyond the drone sightings database mentioned in this work?
Yes, I think everyone is looking at something similar to the ICAO NX 13, where we have the accident database, let's say standardization principles from ICAO, which has to be always obeyed once we have an accident with the aircraft. For drones, so far, that's not yet existing because we are not in the certified environment yet. So we have open and specific category. So this is just a historic blank point. And I think indeed we should enrich ICAO NX 13 and say the same way we're studying aircraft accidents should apply to drone accidents later on. And then we would have something similar to what we were using for the manned aircraft accidents so far. So yes, I think that's a fully valuable question. This drone sighting database is something like a good substitute, but should not be the right selection on the longer way.
Mm-hmm. The severity assessment in the agent-based modeling system is something you haven't done yet, at least not in a very detailed fashion. Is that something you are planning to do, and how would you go about it?
Yeah, seriously, because what we were showing, I think everybody was looking carefully on the presentation, was wondering about the high probability values, which definitely relies on the very critically designed scenario where we have something like collinear movements between drones and an aircraft. So that's why the data is that dramatically looking. But what we also should make clear once again is what I tried to show with that ICAO risk matrix, that it's all about now the severity limitation. So to say, where is the risk allocated within that box? And that's why a severity implementation or modeling in the agent-based modeling simulation is very important. What we actually do is that we will then unlock some of the parameters from the collision envelope we call it. So that is no longer locking, let's say, the track of the drone to the track flown by the aircraft, minus 180 degrees. So to provoke a head-on conflicts, right, as I was saying in the talk. So we would arbitrarily let the drone, if you like, swallow from the left to the right, up and the down, and so we would have distributions. So the agent drone would receive another dimension of freedom, and this would be then the lateral and the vertical fluctuation in its heading, and then would finally lead to a statistically degraded severity when it comes to a hit, to a collision. And that's why we would pursue this. Reflecting to the previous talk from Henk, we must be fully clear and very sensitive and not, let's say, putting too much free variables in an agent-based simulation, because a similar effect as we do have for the Monte Carlo simulation. So it is really then becoming very time-consuming. But so far, I think this is something which should be considered, and we are actually preparing us for doing these trials.
Mm-hmm. And if you would knock on the regulator's door and propose that your methodology would be included in assessment techniques such as SORA, how would you do that?
Yeah, maybe to recall what we do actually in the according to EASA is saying whenever we have something which is being operated in an urban environment and is heavier than 4 kilograms, or outside an urban environment is heavier than 25 kilograms, we have to execute something what we call a specific type operational risk assessment. And finally, it is just trying to, in a very complex way, to figure out how much is the so-called air risk, so the collision probability of the unit to be operated with the environment. And then we have something what is a ground risk, so how much, let's say, threat is imposed to the ground, close to what was Henk let's say, presenting, yeah. So and the combination of the ground risk class and the air risk class comes to what it's called then the let's say integrity level, SIL, and this is then simply split into high, medium, and low. And if it's low or medium, then it can be accepted by the authority to say, okay, you can execute that operation. It's okay the way it does. But what we think is if it comes to much more operations, we can no longer work with these classifications ideas. But I think it would be very interesting to have something like a fast simulation, which allows us to very specifically assess that risk. And the part we were actually doing in the paper would then be the air risk, and probably enriched by something what Henk is presenting on the ground risk. And this then would combine a much more specific answer to what is a risk executed or endorsed by that operations. So this is what we're looking at. And I think it could be very interesting to show the comparison between these SIL levels, which are actually being used, and the outcome from our simulation. Yeah, so that's the way we're trying to approach the problem.
Excellent. Thank you very much. Hartmut, danke. Henk, bedankt. Thanks to both presenters. Thanks to the audience. We have a coffee break now, and we'll be seeing you back at 5:20. Enjoy your coffee.
Thank you all.